Hi, in this video we're going to be talking about diagonalization. So diagonalization is something that you can do to a matrix to write it in another form, but before we get to exactly what that looks like, let's start out looking at this example right here. So B is this 2 by 2 matrix, and the goal is to find B raised to the 10th power. Okay, so if we start this process, we can square B by just multiplying the matrix by itself, and then we get this nastier looking matrix. The next step would be to find B cubed, and we would get this nastier looking matrix still. There are some shortcuts we could go about, like for example, taking, instead of B cubed here, we could just square this matrix again to skip over to B to the 4th. And then we could square that to jump to B to the 8th, and then we'd go back and multiply by B squared again. So there are some shortcuts, but the idea is that these numbers are getting nasty and there's no clear pattern on what these numbers are, and we're going to try to find a way around that so that we can relatively quickly and easily raise a nasty looking matrix to a high power. So here I just wrote 10, but that 10 could just as easily be 100 or 1,000, and we want to be able to do this efficiently. So let's take a look at this different looking matrix here. So this matrix is 2, 0, 0, negative 3, and the goal is the same thing. We want to raise this to the 10th power. And just looking at a squared here, when we multiply this matrix by this matrix, right, we have 2 times 2 plus 0 times 0 giving us this 2 squared up here. These off-diagonal entries are always going to be 0 because they come from 0 times something non-zero plus something non-zero times 0. So the next diagonal entry is going to come from 0 to 0, negative 3, dotted with 0, negative 3. So this 0, negative 3 dotted with that 0, negative 3 is giving us negative 3 squared. So what's happening here is every time we increase the power, every time we multiply by one of these A matrices, we end up just multiplying this entry by 2 and this entry by negative 3. If we had non-zero entries here, they would also get scaled by these numbers according to what column they're in. But for now, let's just say that the diagonal entries are all getting raised to the corresponding power. And so this pattern does continue, and what that means is that A to the 10th is just going to be this matrix, 2 to the 10, 0, 0, and negative 3 to the 10, which is the same as positive 3 to the 10, but I'm not going to worry about that now, nor am I going to worry about what those actual numbers look like when written in base 10. So, why is the matrix A easier to raise to high powers than B, right? This pattern is very nasty, which is why I stopped. And we will come back to this. So let's talk about why A was easier to raise to a power. So one thing you could say is that A is diagonal. So the only non-zero entries in A are on the diagonal, on the main diagonal. Okay. A second, slightly more complicated thing you could say is that if you look at the eigenvectors of A, they are just our standard basis vectors. And A is represented using the standard basis. So when I'm talking about A as a linear transformation of R2, I have to say that the first column of A is the image of the first basis vector in the standard basis. And the second column of A, 0, negative 3, is the image of the second basis vector, E2. Let's actually find the eigenvalues and eigenvectors of A now. So here we have A minus lambda I, so I've just subtracted a lambda I from the main diagonal, just like we always do for this. And now I'm taking the determinant, which is the product of this and this, minus the product of this and this, which I'm leaving off because it's just 0. And we get this, and we're setting it equal to 0. And that tells us that the eigenvalues are exactly 2 and negative 3. In other words, just the main diagonal entries. We could have also been able to tell that that 2 and negative 3 were the eigenvector or eigenvalues of this because this is a diagonal matrix. Okay? And all diagonal matrices are upper triangular, and all upper triangulars have eigenvalues which are just the diagonal entries. So we get 2 and negative 3, and now let's just look at 2 for now. If we take 2 off of the main diagonal, we're going to be left with a matrix that looks like 0, 0, 0, negative 5. And if we're trying to find the eigenvector that corresponds to lambda equals 2, then we just need to write down what this means for the eigenvector, right? We're trying to multiply this matrix by some non-zero vector to get 0, so we augment with zeros here. We can say this is the number of x's, this is the number of y's, and then we can write down, this first equation says that 0x plus 0y equals 0. That doesn't really tell us much. The second equation says that 0x minus 5y equals 0. Okay, well, the 0x part doesn't really help us, but it at least eliminates the x. And we get that negative 5y must be 0. In other words, that y must be 0. Okay, so y must be 0, and x can be anything. So we're going to get the vector, we'll just say x times 1, 0. Or if you want, we can just say that's x 0. So any vector of this form is an eigenvector with lambda equals 2 as the eigenvalue. So I'll just say similarly, for lambda equals negative 3, we get 0y as the eigenvector. Okay, so now let's look at another way to view this a to the 10th power to see why exactly the second condition here is making it easy to compute a to the 10th power. So I'm going to think of a to the 10th power as a transformation, and I'm going to look at what that transformation does to an arbitrary vector in R2. So another way to solve this is to say, what would a to the 10th do if I multiplied it by xy? Well, a to the 10th times xy is the same thing as a to the 10th times x0 plus 0y. Another way of saying this is I'm breaking up xy so that it's a linear combination of eigenvectors. And we could leave it like this, just to give you another option though. We could use the actual basis vectors here and factor out the y. The only thing the x and y, the only thing we care about here is that we have a linear combination, so we're allowed to have coefficients. Okay, so this vector that we're applying a to the 10th to is still the same vector xy. I've just written it in a different format. And what can we do for this? So we know that these vectors are eigenvectors of A, and so we can distribute this a to the 10th in and apply it to each one of these vectors individually. So a to the 10th times x, which remember is just a constant, times 1, 0, and then plus a to the 10th times y, another constant, times 0, 1. Okay, so this constant you can think about as coming out to the outside. So I'm going to write this as x times a to the 9th, and then times a times 1, 0. And I'm going to write this one as y times a to the 9th times a times 0, 1. Okay, so this is sort of a weird thing to write. But just to note, I still have everything in there. I have 9 factors of a here. I'm trying to say what happens when I take one of those factors of a and apply it to the vector. Okay, and the reason this will look nice is because I know that this is an eigenvector of this matrix. And so when I apply a single factor of a to this matrix, it's going to just multiply by the eigenvalue. Remember, the eigenvalue for this was lambda equals 2. Okay, so the x moves past the matrices, or you could leave it up here. It doesn't really matter because x0 is also an eigenvector. So I did the same thing over here, and let's see what this does. So I get x times a to the 9th, and then a times 1, 0 is just doubling this vector, 1, 0. Turns it into 2, 0. Here we get y times a to the 9th, and then a times 0, 1 is the same thing as negative 3 times 0, 1. And so we're just going to get the vector 0, negative 3. Okay, well, these vectors here, 2, 0, and 0, negative 3, they're both still of the correct format to be eigenvectors of this matrix A. And so I pulled off one of these 10 factors to apply it to the vector that we had, and now I can pull off another one and apply it to these new vectors, and I can keep doing that. Each time these entries will double, and these entries will be multiplied by negative 3. So what we're going to end up with, I'll just say dot, dot, dot. After we do this 10 times, we're going to end up with x times, these things got doubled 10 times in total from the original numbers. And so we get 2 to the 10. And then 0 doubled 10 times is just 0 still. And this is going to be these original 0 and 1 got multiplied by negative 3 10 times. And so we're going to get 0 and then negative 3 to the 10. Okay, and let me just write down, this is the vector x times 2 to the 10 and negative 3 to the 10 times y. So a to the 10th is a transformation which takes an arbitrary vector, and in the end it's going to output 2 to the 10th times x, negative 3 to the 10th times y. And if we find a linear transformation in matrix format that does exactly that to an arbitrary vector, then we've found a to the 10th. And the matrix that I had written down before is exactly the only matrix that will do this. It's the only matrix that takes an arbitrary x and y and always multiplies the first coordinate by 2 to the 10th and always multiplies the second coordinate by negative 3 to the 10th. Okay, so that's exactly raising the diagonal entries to the power 10. Okay, so that's another way we could have seen it. And the only thing we had to use for this is the fact that the eigenvectors were the basis elements. Okay, so we just expressed the arbitrary vector here, xy, in terms of our eigenvectors, so as a linear combination of our eigenvectors, and then this whole process worked, and we got out that in the end we just had to multiply the x and the y by this nice thing. Okay, so what I'm trying to say is you can think about either of these two as being the reasons for A being nicer than the matrix B that we had before. Let's take another look at the matrix B. So recall that B was this matrix here. And if we can write B as the product of three matrices in this format, where notice that the first and last ones are inverses of each other, and the middle one, D, is diagonal. Okay. Just to note here, we'll be thinking about P as a change of basis matrix. So that will mostly just mean that it's invertible, but later on we'll see that it's actually referring to a specific basis. So when we take this and we raise B to a power, we can think about multiplying B by itself. So we have B times B. So this is B, and this is another B. And when we multiply B times B, something nice happens. This P inverse times P will cancel each other out, and we'll just be left with P times D times P inverse. In other words, we just have P times D squared times P inverse. Okay, so this is a nice way of writing B squared, and notice that the format doesn't change. We still have this P and P inverse, and D squared is something that's easy to compute because D is diagonal. Okay, so if we want to do the same thing for B cubed, we can take the result that we just got here, put it in right here for B squared, and multiply by B again. So B times B squared is, again, we're going to have this P inverse times P cancel each other out, and we just get left with P, D times D squared is D cubed, and then a P inverse on the end. Okay, this pattern continues, right? This is going to happen for B to the fourth, B to the fifth, etc. And so B to the 10th, the thing that we're trying to find is P times D to the 10th times P inverse. So it would be nice if we could do this. It's not always possible to do this, but for this particular matrix B, it is possible. So what are these matrices D and P? Well, D is this matrix right here, 3, 0, 0, 4, and P is this matrix here, 2, 1, 1, 1. Okay? And in order to use this decomposition into a product of three matrices, we need to also know P inverse, which is this matrix here. Okay, so let's just go ahead and check that P D P inverse is actually equal to B. Well, P D P inverse is going to be P times D times P inverse, and D times P inverse, remember this 3 here is just going to triple the first row, and the 4 here is going to quadruple the second row. Okay, and now when we multiply that by P, we're just going to get back to the original matrix B. So I'll leave you to check the actual arithmetic details if you want to, but it does work out. I'd like to point out a couple things now. Our goal for this section is to, in general, be able to determine when these D and P exist and determine what they are, if they do exist. As you may have realized, just as before, these diagonal entries will be the eigenvalues of our matrix. So these diagonal entries are certainly the eigenvalues of D, right, for the same reason as before. This is a triangular matrix, so its eigenvalues are on the diagonal. So 3 and 4 are eigenvalues of D, but notice that D is similar to B, right? B is equal to P, D, P inverse. That's exactly what it means to be similar. So B and D are similar, and any two similar matrices have the exact same eigenvalues. So 3 and 4 are also the eigenvalues of B. So if I wanted to find D, I could just find the eigenvalues of B, list them along the diagonal, and that's it. That's D. Now how do you find P? Well, the goal, in order to actually use this diagonal matrix, is to switch to this eigenbasis. So we want to think about this as a basis of eigenvectors, and the part of D that, say, multiplies something by 3, the something has to be the eigenvector corresponding to lambda equals 3. So what we need to do is make P the change of basis matrix to go from the standard basis that we were in before, that B is written in, and we need to have, well, the first thing needs to be switching from the standard basis into this eigenbasis, and that's what this P inverse does. Then the D matrix is going to do the actual operation with that new basis, where the operation is really nice because it just scales the coordinates. And then finally this P matrix is going to transfer from the eigenbasis back into the standard basis. So we've transferred from the standard basis into the eigenbasis, done the operation, and then transferred back. And so all in all, we've done the operation and we end up with something in our original standard basis. Okay, so how do we find P? Well, P, remember, is the change of basis matrix from the eigenbasis into the standard basis. And so the columns of P should just be the eigenvectors. In other words, the basis vectors in the eigenbasis. Okay? So 2, 1, and 1, 1 are the eigenvectors of the matrix B. Okay? And then P inverse would be calculated once you know P. So now it's time to actually write down what B to the 10th power is. So recall that we said that B to the 10th is going to be P times D to the 10th times P inverse. So that's what we have here. And we know what P and P inverse are. D to the 10th, remember D is diagonal, so raising it to the 10th power is just going to be the same thing as raising each of the diagonal entries to the 10th power. So we get 3 to the 10th and 4 to the 10th. Again, I don't care what those numbers are specifically here. I'm just going to leave them in this format, 3 to the 10th and 4 to the 10th. Okay. So I'm going to combine these two matrices first. Remember, this 3 to the 10th is just going to multiply this row by 3 to the 10. So we get 3 to the 10 and negative 3 to the 10. And this 4 to the 10 here is going to multiply the bottom row by 4 to the 10. So negative 4 to the 10 and 2 times 4 to the 10 here. Okay, and now multiplying this matrix in, we're going to get 2 times this plus 1 times this. That's our top left entry. Okay, 1 and 1 here just means we have to add these two together to get this bottom entry. And then let's see, 2, 1 dotted with the second column is going to be 2 times this plus 1 times this. That's this. And then finally the sum of these two entries is going to be the bottom right entry. Okay, so that is B to the 10th. It may look ugly, but it is a nice format, and it's certainly nicer than having to multiply the matrix by itself 10 times. Let's take a look at another example. So recall this matrix A from the last video, and we found there that the eigenvalues are 3 with multiplicity 2 and 8. And we also found a basis for the eigenspace for lambda equals 3, were these two vectors right here. And because they're a basis, they are linearly independent. And I will point out that this is very important. We need this linear independence for this process to work. For lambda equals 8, we get this as an eigenvector. And let me show you how to get that. And I'm going to include a shortcut in this. So when you do a minus 8 lambda, we already know that 8 is an eigenvalue for this. So we know that this matrix is not invertible. And because each pair of vectors is linearly independent, in other words, this is not a multiple of this, nor is it a multiple of this. This is not a multiple of either of the other two, and this is not a multiple of either of the other two. Then the dependence must be one vector is written as a linear combination of the other vectors. And you could say that about any of these vectors. So the first row is some linear combination of the second and third rows, and the second row is a linear combination of the first and third rows, etc. So one thing you can do while you're row reducing this, because you already know that this is not invertible, and no two rows are multiples of each other, then you can just eliminate one of these rows, right? This has to be row equivalent to, well, let's just say I don't like this top row for whatever reason. I can just replace it with all zeros. Okay, so I'm going to zero out that top row, and let's keep this row. Or maybe let's get rid of the negative signs, scale it by -1. And now let's replace the third row by the third row plus 2 times the second row. So that's going to make this 0 here. 2 plus 2 times -1, and then 2 plus 2 times -7. Oh, sorry, 4 plus 2 times -7 is going to be -10. And 1 plus 2 times -3 is going to be -5. This is all of the row reduction you have to do, except for maybe scaling this last row by -1/5 might be nice. But the idea here is that you already have exactly what you need. So say this is the number of A's, B's, and C's. We're also thinking about this being augmented. And we want to say that this row says A plus 7B plus 3C equals 0. In other words, A is equal to -7B minus 3C. And this row says that -10B is equal to 5C. Or B is equal to -1/2C. Okay, so we're going to start out by picking a convenient value for C, and I'm going to choose, well, I'm going to choose this C right here, +2. And the reason I chose that was because I want this fraction to cancel it out and make it an integer when we solve for B. So if C is 2, then we're going to get B is -1/2 times 2, in other words, -1. And A is going to be -7 times the value of B that we just determined, minus 3 times the value of C that we set. Okay, so -7 times -1 is +7. +7 minus 6 is 1. So that gives us A, B, and C. 1, -1, 2. That's this vector right here. So hopefully you can use this shortcut in the future where you just pick a row that you don't like and eliminate it. The only condition that you need to have to use that shortcut is the remaining 2 rows are not allowed to be multiples of each other. unless you already happen to know that the multiplicity of the eigenvector you're looking at, or the eigenvalue that you're looking at, is more than 1. Now on to the stated problem. Our goal is to find a diagonal matrix D and an invertible matrix P so that A is written in this diagonalized form, right? This process of finding the P and the D is called diagonalization. Okay? So the P and the D are going to be just as they were before. They're going to be the eigen vectors forming the columns of P. So I'm just going to write those down. So negative 2, 1, 0, and negative 3, 0, 1. Negative 1, 2. So we have that, and D is the diagonal matrix, which is made up of the corresponding eigenvalues. Okay, so the diagonal entries here are going to be the eigenvalues 3, 3, and 8. And the only thing you need to make sure of when you're writing these down is the order matters here. So the 3's have to correspond to the eigenvectors for lambda equals 3, and the 8 has to correspond to the eigenvector with lambda equals 8. And I wrote the eigenvector with lambda equals 8 in the third column here. And so the 8 has to go into the third column here. Okay, and the 3's are up there. So the order has to always match. If you have first, second, and third eigenvector, then you need the corresponding first, second, and third eigenvalues. Okay. One thing we need to make sure of is that P is invertible. Now, you could just plug it in this particular case to see that it's invertible, but just to note, what it means for P to be invertible is that these 3 vectors here are linearly independent. Okay? So we know that these 2 vectors are linearly independent because they formed a basis for the lambda eigenspace for lambda equals 3. How do we know that this third vector, when combined with these, is also going to maintain the linear independence? Well, that comes from the fact that this lambda equals 8 is not the same as lambda equals 3. And there is a theorem that we'll see in the next video that says if you have 2 distinct eigenvalues, then their corresponding eigenvectors must be linearly independent. So we'll see that next time, but it's relevant for this example, and it shows us that P is invertible even without having to find the inverse. Although, to write it in this form and actually use that, we would need to just find the inverse anyway. Just to note, this is not the only answer. So we could have instead come up with a different answer that looks something like this. So I'll call these P1 and D1. And the way I'm going to get P1 is I'm going to switch the second and third columns. And while I'm at it, I'm going to double this column. So I'm going to make this 2, negative 2, and 4. So just to note, we're allowed to scale any eigenvector and still have an eigenvector with the exact same eigenvalue. And so our choice of this particular eigenvector was completely arbitrary, right? It happens to be the smallest scaled version of this that involves only integers up to sign. But if I double everything, I mean, sure, everything's even now, but it's still a perfectly good eigenvector, and there's no real reason to prefer this one over that one, at least for purposes of doing this problem. The fact that I've switched these two means that I need a new diagonal matrix now, because I need my diagonal entries to be in the correct order. So this one, the eigenvector corresponding to lambda equals 8, is now in the middle column, or twice it is. So our diagonal matrix is now going to be 3, 8, 3. There's lots of ways we could change this. Just to note, the answers for these problems are not unique, but they all involve 3 eigenvectors and 3 corresponding eigenvalues in the correct order, whatever order you chose for this. Here's another example. So we have this matrix 1, negative 2, 0, 1, and we're going to do the exact same thing with it. So we're trying to find the matrices P and D. And the first step is to find the eigenvalues of A. So the eigenvalues are just going to be the diagonal entries because this is a triangular matrix. So, strangely worded here. The eigenvalue of A is this. There's only one eigenvalue, and it has multiplicity 2. So, with that, we can now find the corresponding eigenvectors. So the eigenvectors we're going to find by doing A minus 1 times I, right? A minus lambda I, where lambda is 1. And this is the matrix 0, negative 2, 0, 0. Alright, so with this, let's say this is the number of A's, this is the number of B's. We're thinking about this being an augmented matrix. There's no row reduction to do here, it's already reduced enough. And we can say that the first line tells us that 0 times A minus 2 times B equals 0. And the second line tells us nothing, 0 times A plus 0 times B equals 0. Okay, so this line tells us that negative 2b equals 0, which is the same thing as saying that b must be 0. Okay, so a can be anything, and b must be 0, and our vector ab now looks like this. It's factoring out the a, it's a times 1, 0. Okay, so any multiple of this vector right here is an eigenvector of A corresponding to lambda equals 1. But notice that we only got 1 here. We only got 1 eigenvector, as opposed to the last time we looked at a matrix with an eigenvalue that had multiplicity 2. We had a 2-dimensional eigenspace. Here we are only getting a 1-dimensional eigenspace. So just graphing these things, we have our E1 and E2. And the E2, so the E1 is going to itself. So the E1 is staying where it is after this transformation. And E2 is going to negative 2 times E1 plus E2. So this is AE2 over here. So our new square, so if we take this square and we apply the matrix A to it, we're going to get something like this parallelogram here. Didn't draw that very well, but the idea is it's just a sheared over version of the original square. And when that happens, something weird happens with the eigenvectors and eigenvalues. Every point in the top part of the plane gets moved left, every point in the bottom part of the plane gets moved right. And all the points along the x-axis here are going to stay where they are. In other words, a scaled version of this point is a point on the x-axis, and it stays where it is, corresponds to an eigenvalue of 1, and every other point gets moved left or right. And moving left or right, unless you're on the x-axis, is not a scaled version of a vector. And so nothing else is going to get scaled when this happens. In other words, there are no other eigenvectors because everything else is moving off of its span. In order to form P, we need enough linearly independent eigenvectors to form a matrix out of. And what that means here is we need 2 of them. We only have 1, and what that means is we can't do this. So this problem has no solution. Another way of saying that is this matrix 1, -2, 0, 1 is not diagonalizable. The easiest way to say why is if it were diagonalizable, we would get a diagonal matrix, a 2x2 diagonal matrix, and the eigenvalues would have to be the diagonal entries. So we'd have to have 1 and 1 because those are the eigenvalues of this. Remember, the diagonal matrix corresponding to this has to have the exact same eigenvalues. So we'd get this diagonal matrix, the identity, and then we'd have some P and P inverse, and this is supposed to equal our original matrix. But this is impossible because the identity times P is just P, and then P times P inverse is just equal to the identity. It's not equal to this. So this can never happen. And the general rule is that in order for something to be diagonalizable, you need the matrix to have enough eigenvectors to form a basis. So you need an n by n matrix to have n linearly independent eigenvectors. And it turns out that is exactly what you need. If you have that, then it is diagonalizable. If you don't have that, then it's not diagonalizable. Thank you for watching.